I'm crushing it today. That's the second time. She missed it. What was that?
Number 1 to 2.
I think it just, did this just turn off? 2D linear momentum. Actually, let me start differently here. They just went to sleep. Don't worry, everybody. It's not going to blow up. There, 5 questions. Don't. No bonus. You don't need a bonus. All right. Questions? Deuces. Bottom goes from potential to kinetic, right?
Yes.
All of it, if there's no friction.
Yes. If it is applicable to number 3, then yes, I would vote do it. On the
test
final.
2. All right, let's do this.
That's like a circle.
A what? Number 5.
Number 5
Number 5.
on test 2 is applicable to number 3 on the final.
Oh, okay.
All right, listen up, you guys.
Yes, guys.
That's the one for
All right, hey, this is number 5 on test number 2. Remember we had 2 boxes, one on a steep ramp and another on a shallower ramp, not so steep. And they were both at the height h, essentially, off the ground. If it's frictionless, remember I always start here when I'm talking energy conservation. If it's frictionless, this would be 0, which implies what? E final equals E initial. What I end up with equals what I started with. Well, what am I starting with here for these things? If this is M and this is twice as heavy, for example, what's the energy in the system for this one? Yep. mgh. How much, if it's right there stationary, how much kinetic energy does it have? 0. At the bottom of the ramp, how much potential energy does it have?
0.
How much kinetic energy does it have? All of it, right? Notice the masses will cancel, and the velocity at the bottom is 2gh, and I take the square root of that mess. That's for the first mass. Now if I do this with the second mass, how much energy is in the system for this guy? 2mgh. And then at the bottom of the ramp, if it's frictionless, all that energy goes to kinetic energy. 1/2 times 2mv squared. What do you notice? The masses cancel. So the velocity at the bottom is 2gh. Square For that problem, if it's frictionless, makes no difference. That, if it's frictionless, I have this scenario. If there is friction, there's going to be a difference between what I started with, what I end up with and what I started with. And this delta, this difference will probably be, if there is friction, will probably be no one's answering me. Pay attention! If there is friction in the system, this difference will probably be negative. I'll end up with less energy than I start with. Where does the rest of it go? It's work that's done by friction. Yes? Okay. Does that seem reasonable?
Yes.
Yeah, this is real life. This is physics world, right? Almost everything has friction, and we lose energy from our systems that go to friction, air resistance, and that kind of stuff. So that problem was testing to see if you understood the idea that if there's no friction in a system, this is true, and the masses disappear. If there is friction in the system, now I'm going to have to redraw this. God! The work I have to do. If there is friction, for say this guy here, right? It would be final 1/2 2 3 squared minus 2 h. If I knew all of this information, if I knew the velocity at the bottom of the ramp, I can figure out the kinetic energy at the bottom. I can guarantee you if there's friction on the ramp that this number will be less than this number because some of that energy goes to friction. That minus that tells me how much energy goes to friction because this is joules, that's joules, and that's joules. So joules minus joules gives me joules, and I know how much energy's been taken away from the system. Okay?
Great.
Yay!